swung very slowly, and the deviations are now noted on at least 8 equidistant headings. Most of the compass adjuster now do it every 10 degrees, and they check that all the coefficients have been reasonably corrected. Then we record a table of deviations remaining uncorrected. Along with the deviations, we note down the latitude and longitude of the place where the correction is done, the date when the correction is done, the time, and also the position of all permanent magnets with their directions. For example, for a fore and aft magnet, the marking which is made on the deviation card is, say for example, red forward or blue to starboard for a outward shape magnet and blue upwards for a healing error corrected magnet. The position of the healing error bucket and the length of the flinder bar and the scale position of the soft iron spheres are all noted down in the deviation card. Also, the value of variation which is there at that location, present at that location, which was also used to carry out the adjustment, is also noted down in the deviation card, thus completing the correction of the compass and preparation of the deviation card. The compass needle, right angles to the magnetic lines of force, and it will generate maximum deviation, and this heading will be 075 degrees. So this is one option. Now there is one more possibility of bringing the resultant to east or west of the compass. Instead of bringing it to west of the compass, we can also bring it to the east of the compass. Now to bring the resultant east of the compass, the resultant has to move in the direction of this new arrow, yellow color arrow now, which represents 105 degrees. So if the ship changes its heading or swings in the anti-clockwise direction by 105 degrees, this resultant is going to come exactly east of the compass, exactly east of the binnacle. And that tells us that if we do a alteration of 105 degrees to port represented by the red color arrow, if we do a alteration of 105 degrees to port, the resultant would be exactly east of the compass needle at right angles to the magnetic lines of force, generating maximum deviation. Now, if you swing 105 degrees to port, the heading will be 255 degrees. So the second heading is 255 degrees. If the ship heads on 255 degrees, resultant will be exactly east of the compass, generating maximum deviation.
So, but for 255, we should note that our present heading should be said northerly, na? But it is not given that our present heading is 000.
Beta, they have asked us on what headings should the correction be done. So whether your present heading is 0 or 90 or 270 does not matter. The two headings on which the
Okay,
correction
okay.
should be done is 075 and 255.
हाँ जी हाँ जी ओके समझ गया सर
Okay.
ओके सर
Okay, beta. Great. Now understand the healing error present in the magnetic compass. Healing error is the difference in deviation between that when the ship is in the upright condition and that when the ship is heeled or listed on the same course. To give you an example, if the deviation is observed to be 5 degrees east when the ship is upright and the deviation is 7 degrees east when the ship is heeled heading on the same course, the difference between these two, 5 degrees east and 7 degrees east, that is 2 degrees east, this difference has been caused because of the heeling of the ship and is known as the heeling error. Now let us go into the cause of this heeling error. When the ship heels or lists, the compass or the compass card still remains horizontal due to the gimbal arrangement present around the compass. Let us understand it from the diagram. Now in this diagram you can see the ship is in upright condition in this particular diagram. The vessel is upright. This is the compass bowl, and in this particular ship we have a permanent magnetic field present in the vertical orientation. You can see we have a vertical magnetic field exactly below the compass card, acting vertically downwards. This particular vessel has the blue end on top closer to the compass and the red end at the bottom. Now a magnetic field acting vertically downwards at the compass location or compass position will cause no deviation when the ship is upright. Now if you have a look in the diagram, the vessel is upright. You can follow the laser pointer. The compass bowl or compass card is also perfectly horizontal, and in this particular situation no deviation is generated. Why no deviation is generated? Because the card is horizontal, the magnetic field is acting vertically downwards, both are perpendicular to each other at 90-degree angle to each other, and being perpendicular, this vertical magnetic field does not cause any deviation at all. Now as soon as the ship heels to either side, now you can have a look in this particular diagram, the vessel is heeled to the port side. As soon as the vessel is heeled, this particular field now acts on the compass at an oblique angle. Why has this happened? The ship has heeled to the port side. We are looking at the ship from the stern. The ship has heeled to the port side, whereas the compass bowl or the compass card still remains horizontal because of the gimbal arrangement. So this magnetic field now acts at an oblique angle. It is no more at right angles to the compass card. And since it acts at an oblique angle, one of its factors, if you consider this magnetic field as R component, and the vessel has heeled by an angle I is the angle of heel, then its horizontal component, the horizontal component of the magnetic field R, which comes to R sine I, is now acting on the compass card. So as soon as the vessel has heeled, there is a component of the R component, R factor, which is acting in the horizontal plane, that is R sine I, and this is what causes the heeling error. You can see in the next diagram, the vessel is having a starboard heel here. The card remains horizontal, and in this case, the horizontal component of this field, that is R sine I, is acting on the compass card now and is generating the heeling error. Now when the vessel is rolling, this oblique field or force acts in opposite direction during the port and starboard rolls, leading to oscillation of the compass card. You can see in this condition the vessel was upright, the vertical field was not causing any deviation. So you can see here no heel, no deviation, there is no deflecting force. When there is a port heel, you see the vessel's hull has heeled to the port side, the compass bowl remains horizontal. The horizontal field of this oblique magnetic field, that is R sine I, now acts to the starboard side of the ship. So you can see deflecting force to the high side, which is the starboard side, and we have a blue pole basically to the starboard side of the compass location, and this blue pole causes easterly deviation. So it is mentioned here also, port heel, the blue pole is carried to the starboard side, generating a easterly deviation. Now when the vessel heels to the starboard side or rolls to the starboard side, This oblique field now acts in this particular direction. You can see R sine I component of the field is acting in this particular direction. So deflecting force is towards the high side, which is the port side. And in case of the starboard heel, you can see here in case of starboard heel, the blue pole is carried to the port of the compass bowl or the compass card, generating a westerly deviation. This blue pole attracts the red end of the compass needle pointing towards north, and it generates a westerly deviation. So when the vessel is rolling to port and starboard, the field acts in opposite direction, leading to oscillations in the compass card. Thus, rolling makes the card swing from one side to the other side, resulting in a very unsteady compass, making the steering difficult. Now, this healing error is composed of two components. Healing error could be generated because of permanent magnetism of the ship. In that case, it is known as permanent healing error. And this permanent healing error is generated due to the force R or component R. In this particular diagram, we see this is the permanent magnetism of the ship, vertical component, R component of the permanent magnetism of the ship, and this is causing the permanent healing error. The permanent healing error varies as cause of the compass course. The second cause which can generate healing error is because of induced magnetism in the ship, and that is called as induced healing error. This induced healing error is predominantly caused due to induced magnetism in two kind of structures. If we have a vertical soft iron VSI above or below the compass, it is also known as a K rod. This VSI exactly above or below the compass generates induced healing error. Just to give you an example, if we have a centerline bulkhead in the accommodation and there are a lot of vertical stiffeners which are welded to that bulkhead, centerline bulkhead, it will have a substantial soft iron component. There will be a induced magnetism and that will generate induced healing error. So this is one structure, VSI above or below the compass. The second structure which can generate induced healing error is the athwartship horizontal soft iron. That is basically the athwartship beams or transverse beams on the ship. So this is also known as a E rod, eco rod. So these athwartship horizontal soft iron also generate healing error. Whenever the vessel heels, one end of the beam is closer to the compass, which is the high side, and one end goes far away from the compass, thus generating the healing error. So now we have seen that the healing error is caused because of permanent as well as induced magnetism of the ship. And as per our correction principle of like cures like, we should be correcting both these components with their respective correctors. That is, permanent should be corrected with a permanent magnet, induced should be corrected with a induced magnet or a soft iron corrector. But able to use this principle. Reason for this is, if we use the like cures like principle, for doing so, the permanent magnets and the soft iron corrector will have to be placed very close to each other. They will be vertically above or vertically below the compass. Since the permanent magnet as well as the soft iron corrector is very close, it will lead to a strong interaction with each other. The permanent magnet is going to generate a lot of induction in the soft iron corrector, making the correction unmanageable. So because of this reason, both these effects, permanent healing error as well as induced healing error, are therefore corrected by using permanent magnets placed below the compass card. Correction is achieved by keeping the permanent magnets in a healing error bucket, which has a counterweight and pulley arrangement. Let me show you in the diagram. You can see the diagram of the healing error corrector. We see we have the compass card in this particular location, and this is the binnacle. We have a permanent blue pole. You see ship's blue pole below the compass. In the previous slide example, we saw that there was a blue pole exactly below the compass. So now what we have here is exactly below this compass card, we have a chain and pulley arrangement. You can see we have this pulley here, or you can call it a sprocket wheel, and we have a chain attached to this wheel. On one end of this chain, we have a counterweight just to balance the healing error bucket. We have a counterweight here, and on the other end of the chain, we have the healing error bucket. There are vertical slots in this bucket in which the magnets can be placed. So we place vertical magnets in this bucket. You can see there are these vertical magnets placed in the bucket. The magnets are placed in such a way that the corrector end should be closer to the compass card. In this particular example, we had a blue pole of the ship which was affecting the compass. So we have placed the permanent magnets in such a way that their red pole is closer to the compass card, thus correcting the healing error. So this is the healing error bucket. You can see the vertical magnets placed inside the bucket. If you have a plan view of the bucket, or you look from top, you will see the bucket will look something like this. All these are slots in which the magnets are placed vertically. So plan view of the healing error bucket showing the slots for vertical healing error corrector magnets. Now, why do we have this sprocket wheel or pulley and the chain arrangement? This arrangement basically helps us to vary the magnitude of the healing error correction which is required. The bucket can be raised or lowered as per our requirement. The compass adjuster can place the magnets in the bucket, and then he can raise the bucket or lower the bucket and see what magnitude of correction is required. Then we have a locking arrangement in the sprocket wheel. Once the bucket is properly corrected in the right position, the sprocket wheel or the pulley is locked in location and the healing error is corrected. Now, since in this correction we have not been able to follow the like cure like principle, this error is going to hold good only for the latitude in which it is corrected. And as soon as the latitude of the ship changes, the error is going to reappear. So that's because in whichever latitude you have corrected the healing error, as soon as the ship changes the latitude, the induced healing error is going to change. But our corrector is a permanent magnet, the correction will not change. So either it will be overcorrected or it will be undercorrected, leading to the healing error getting generated as soon as the latitude changes. If a ship has a very strong induced healing error component, if it crosses the equator, goes from one hemisphere to another, when we go from one hemisphere to another, north to south or south to north, the direction of the Earth's magnetic field changes. In southern hemisphere, magnetic field lines come out of the Earth structure. In northern hemisphere, magnetic field lines go into the surface of the Earth. So if a ship has a substantial induced healing error and it crosses the equator, this correction will need to be done again. Because the induced healing error has changed, we will need to redo the healing error correction. Otherwise, it will make the compass card oscillate when the vessel is swinging, and it will be very difficult to steer the ship. Now, going further into the correction of healing error, as per the theoretical correction method, the ship is made to heal when it is heading north, and when the ship is made to heal, the healing error is generated. The card deviates, indicating the presence of the healing error, and whatever is the healing error, this can then be corrected using the magnets in the healing error bucket. Now, practically, this method is going to be very time consuming and cumbersome. It is going to take a long time to heal the ship to one side, and we need a substantial heal angle to properly judge the healing error and correct it. So instead of healing the ship, we assess and correct this error with the ship upright. So how can we judge this error in the upright condition? For this, we use a special instrument which is known as a vertical force instrument, in short a VFI. So for assessing the vertical field at the compass location, we use an instrument called the vertical force instrument. Let me show you the diagram. A vertical force instrument, or a VFI, is very similar to a dip needle. A dip needle is free to move in the vertical plane, and wherever on earth it is placed, as soon as it is released, it is going to align itself in the direction of the magnetic field lines, giving us the dip angle. So this VFI is also very similar to a dip angle. We have a knife edge support, and on this knife edge support we have a magnetic needle. This magnetic needle is free to move in the vertical plane. So one end, this is the blue end of the magnet, and this is the red end of the magnet. On this knife edge support, it is free to move in the vertical plane. So what the compass adjuster does is, he first takes the VFI, vertical force instrument, and he places it at some place ashore, away from any disturbing magnetic field. So when it is placed in an area where there is no disturbance of any magnetic field, this needle is going to align itself in the direction of the Earth's magnetic field. In the northern hemisphere, the red end will be pointing downwards. In the southern hemisphere, the red end will be pointing upwards. Now there is a slider weight which is provided on this needle. You can see this particular weight here. This weight can be moved in whichever location we require. There is a scale also provided. We can see the scale location of the weight. So what is done is, let us assume that we were in the northern hemisphere, and this red end of the needle has gone vertically downwards. This is pointing downwards in the direction of magnetic field line. The blue end has gone upwards. So this weight is initially placed exactly on top of the support, and as soon as the needle stabilizes with the blue end pointing upwards and red pointing downwards, we slide this weight to the high side. So we slide it towards the blue side. Now you see the force of gravity is going to counteract the force of the magnetic field, and this blue end, which was pointing upwards, will slowly come down. As you take the weight away from the support, the lever at which the weight is acting increases, and it starts to balance the magnetic field. And there is also a spirit level indication which tells us whether the needle is horizontal or not. So as we move the weight, we keep on checking the spirit level indicator, and we take the weight to that location where the needle becomes horizontal. So you see, in this particular location, the weight is trying to pull the blue end downwards. Magnetic field is trying to take the blue end upwards. Both are balanced exactly equal to each other, and the needle is horizontal. So in this case, it is known as a balanced vertical force instrument. The VFI has been balanced. Once the VFI is balanced in this particular way, the compass adjuster keeps it carefully in the box, and he now brings this box on the ship, and he places this box or this VFI, vertical force instrument, in the compass location. The compass bowl is lifted up from the binnacle and placed on the side, and this VFI is made in such a way that it can fit exactly in the compass location. So this VFI is placed in the compass location. Now, if there is any vertical field in the compass location, the needle will not stay horizontal. If there is any vertical field, the needle will start to point up or down. So if the needle does not stay horizontal, it immediately tells us that there is a vertical field in the compass location. What the compass adjuster now does is, he does not touches the weight and the needle. He places the healing error bucket and he places the magnets in that bucket. The magnets are placed in such a way that this VFI needle should become horizontal again. So he adjusts the magnets, which red or blue pole has to be put upwards or downwards, and he adjusted the distance of the healing error bucket from the compass location so that this VFI needle becomes horizontal again. When the VFI needle becomes horizontal again, we can check it from the spirit level. As soon as it becomes horizontal, this tells us that at the compass location, the vertical magnetic field has been counteracted by the healing error bucket. So whatever magnetic field was present, vertical magnetic field at the compass location, which was causing the needle to go up and down, has been corrected now using the healing error bucket. So same thing is mentioned here. First, the VFI is placed ashore away from any disturbing magnetic field. It is adjusted or balanced. That means the needle is made horizontal by counteracting the magnetic field with the weight. And then it is brought close to the compass or brought in the compass location. The dipping couple acting on the needle is indicated on the instrument, giving us an assessment of the vertical field, which is corrected using the healing error magnets. A, B, C, D, and E, and we have seen how they are corrected individually. Now we are going to see when a compass adjuster actually corrects the compass on board, what is the sequence he follows in correcting the compass and what are the steps involved in the correction. The first and foremost important thing to consider for the compass corrector is the order of placing the correctors. We have correctors for correcting different coefficients. The first thing which we need to analyze is what should be the order in which the correctors should be placed. We cannot place them as per our liking and choice. We do not have a choice here. They have to be placed in a specific order only. This order is, first of all, the soft iron correctors are placed in the compass binnacle. And in these soft iron correctors also, we have the flinders bar followed by the spheres. After placing the soft iron corrector, the next correction which is done is the healing error correction. So permanent magnets are placed in the healing error corrector bucket. Error is corrected. After the healing error correction, the next correction which we do is placing the horizontal magnets to correct permanent B and permanent C. The larger coefficient out of two, that is between permanent B and permanent C, is corrected first and the weaker coefficient corrected later. This is the sequence what we follow for correction. This specific sequence, there are certain advantages which we achieve when this sequence is followed. The first thing, why the flinder bar is placed before the spheres. Though the flinder bar is used mainly to correct the induced P coefficient, it also provides a small correction for coefficient delta, coefficient D. When the spheres are placed after the flinder bars, this additional effect is compensated and we ensure that the coefficient D is not over corrected. Second, why the soft iron correctors are placed before the healing error permanent magnet correctors. The soft iron correctors partially correct the healing error. So once you place the soft iron corrector, the healing error is corrected partially, and whatever healing error remains can then be corrected by placing the healing error correctors. In case the soft iron correction is not done before, the healing error correction will be overdone. The healing error will be over corrected. Now the third concept, why do we place the soft iron correctors before the permanent correctors, that is permanent B and permanent C? The soft iron spheres increase the mean directive force at the compass location, thus allowing for a more accurate correction of permanent B and permanent C later on. As the spheres are placed, the mean directive force at the compass location increases. This increase in the mean directive force result in reduction of the deviation because of any coefficient. So this gives us a more correct or more accurate correction for permanent B and permanent C. The permanent correctors also induced some magnetism in the soft iron correctors, causing a disturbing field at the compass location. When the permanent magnets are placed after the soft iron correctors, the adjuster is able to compensate this disturbing field. Now, the permanent magnets also induced some magnetism in the soft iron correctors. Since the cause is the permanent magnet, when it is placed later on, the permanent magnet can be adjusted so that this extra induction does not cause any disturbance in the compass correction. Now there are many variations in the methods which we use for compass correction. Some method are used to correct the compass, a brand new compass where there are no correctors placed for a brand new ship. And some of the methods are used for adjusting the compass later on, a partial adjustment. Now, what we see here is the analysis method which is used for a full scale correction of the compass. That means if we have a brand new compass without any correction placed on board, the analysis method can be used to correct that compass and prepare the deviation card. So in this method, deviation is observed on various headings, analyzing the coefficients and then making the corrections in the order of placing correctors as we discussed in the previous slides. Once the correctors are placed, the ship is re-swung to check for any large deviations left and finally leaving only a small amount of deviations. So with the order of placing correctors clear in our mind, let us now go into how each of the corrector is evaluated and placed. So first of all, we go for the flinder bar. This is the first corrector to be placed. Now it is very hard to calculate the exact amount of flinder bar that will be necessary or required in a particular ship and compass. We do not have any precise instruments, so the experience of the compass adjuster comes very handy to him, and this guides the compass adjuster about the length of the flinder bar. As a general rule, sufficient flinder bar is placed to correct 3 to 4 degree deviation when the ship is heading in a easterly or westerly heading. In case the funnel is very close or it is far away from the compass location, the correction magnitude has to be varied accordingly. When the compass adjuster approaches the ship, he looks at the structure of the ship and he gets an idea what is the location of the funnel with respect to the compass, what is the distance between them, and if he finds it a normal distance, a regular distance, he will do the correction of up to 3 to 4 degree of deviation. However, in case he observes that the funnel is too far away from the compass or the funnel is very close to the compass, he will vary the amount of correction by the flunder bar. The second determining factor could be the size of the funnel. Now this 3 to 4 degree deviation is for a regular funnel of a handy medium size funnel. In case the funnel of a ship is too large or too small, in that case also the correction is adjusted accordingly. Now the next correction after the flinder bar are the soft iron spheres for correction of coefficient D. For placing the spheres, the compass adjuster needs to obtain the deviation on all the cardinal and intercardinal heading. So before he goes ahead with the correction, he swings the ship a complete round and he notes down the deviation on all the cardinal and intercardinal headings at least. Now these deviation readings help him to ascertain or evaluate what is the magnitude of all the coefficients. We have formulas for the coefficients with which we can calculate their magnitude, and this helps us to ascertain what is the amount of correction we require. Like for example, the magnitude of coefficient D can be obtained by using this formula. Coefficient D is equal to deviation on northeast heading minus deviation on southeast heading plus deviation on southwest heading minus deviation on northwest heading divided by 4. So once coefficient D is corrected and the compass adjuster knows what is the magnitude of correction he needs to make, he takes the ship on any one of the intercardinal headings. Why do we go on an intercardinal heading? We are aware that all the coefficients are corrected on the heading where they are the most powerful. Coefficient D, we are aware, is the most powerful on intercardinal headings and it is 0 on cardinal headings. So the ship heads on any of the intercardinal headings. The soft iron spheres are brought close to the compass location. They are placed on the side channels fitted port and starboard of the compass location on the compass binnacle. The spheres are placed initially in the maximum outstretched position, far away from the compass, maximum distance far away from the compass. Once you place the spheres in the channel, you will see a change in the heading shown by the compass. Then slowly the compass adjuster moves the sphere closer to the compass. Now as the spheres come close to the compass, you see the heading change increasing gradually. Now the compass adjuster brings the sphere to the required distance where the change in heading is exactly the same, which is equal to the magnitude of coefficient D. That is the correction what we require. Both the spheres are usually at the same distance from the compass. If the compass is placed on a normal merchant vessel in a centerline location, both the spheres are equidistant from the compass. Once the required correction is achieved, the compass adjuster tightens the bottom nuts of the soft iron spheres so that they remain firmly in place. And after this, he notes the location as per the scale. A scale is put on both side channels and he notes down the location of the spheres as per the scale, and this is noted down in the deviation card. Next, moving on to the heeling error correction. Now for the heeling error correction, we need the vertical force instrument. Vertical force instrument consists of a magnetic needle which is free to swing in the vertical plane. So first the compass adjuster has to adjust or balance this VFI at the latitude or at the location where the ship is. He balances the VFI at a location which is far away from any magnetic disturbances. Then he brings it on the ship and he judges what is the vertical field at the compass location, and then he corrects it using the healing error bucket. This is exactly what we saw in the healing error presentation. Power line. Now, after the healing error, next are the corrections, permanent B and permanent C. The bigger coefficient is corrected first. So the compass adjuster first judges the magnitude of the coefficient and then uses the magnitude to correct the coefficient. So how do we obtain the magnitude? Coefficient B magnitude can be obtained by deviation on easterly heading minus deviation on westerly heading divided by 2. Once the adjuster has an idea about the magnitude of the coefficient, he can now place the fore and aft corrector magnets. So the ship is uh, made to head on easterly or westerly direction. Ship is on a easterly or westerly heading. This is where coefficient B is the strongest, and the fore and aft permanent magnets are placed to correct the coefficient permanent B. Uh, the magnets are placed two in a row side by side, and the number of pairs can be increased or decreased. Also, the distance of the magnets from the compass location can be increased or decreased as there are a number of slots which are provided in the binnacle. So by varying the number of magnets and the distance of the magnets from the compass location, the compass adjuster can vary the correction for permanent B. The correction of permanent C. So it is done exactly in the same way as coefficient B was corrected using the deviations obtained earlier. First, the magnitude of coefficient C is obtained. The formula for coefficient C magnitude is deviation on northerly heading minus deviation on southerly heading divided by 2. Once the magnitude is obtained, the vessel heads on northerly or southerly heading, and outward ship magnets, permanent magnets, are placed to correct the coefficient C. Now, after placing these correctors, we move to coefficient A, induced C, and coefficient E. Coefficient induced C and E echo are very rare on a normal merchant ship. Hence, any remaining deviation in the compass is considered to be the result of coefficient A. Coefficient A, if any, is applied as an index error. Coefficient A's value can be obtained as the mean of the deviations on at least 4 equidistant headings. If you remember, we had noted down the deviations before starting the compass correction. The deviations are noted. So the compass adjuster now can easily calculate or find out the magnitude of coefficient A by taking mean of deviations on at least 4 equidistant headings. Normally this is done using deviations on 8 headings, that is cardinal and intercardinal, to get a more accurate reading. The authorship soft iron spheres which we have placed to correct coefficient D, they also give us one more beneficial effect, and that effect is the increase in the mean directive force at the compass location or the compass position. Now, more the directive force, better will be the directional ability of our compass. Now, placing these spheres gives us more or increase in the mean directive force at the compass location. When the directive force increases, this indirectly reduces the deviation because of any other cause, because of any coefficient, thus giving us a beneficial effect. Now, how do the spheres increase the mean directive force? Let's understand. Let's first assume that the vessel is on a northerly heading. Now, when the ship is on a northerly heading, you can see the diagram here. When the ship is on a northerly heading, both these corrector spheres, which are in the outward ship direction, They lie to the east and west of the compass location. Now, the compass is at a broadside on position to the sphere magnet. We can see the blue and red ends of the sphere magnet. The axis of the magnet is north-south in this case, and our compass, which lies to the east and west of the corrector sphere, is at a broadside on position. It is not in line with the axis of the sphere magnet. It is at right angles to the axis. So the compass is at a broadside on position. Now in this location, the poles which are generated on the spheres are opposite to the poles of the earth. In the north magnetic pole, we have the blue polarity, whereas the north side poles of both these corrector magnets are having red polarity. Likewise, the south magnetic pole of the earth has red polarity, whereas the south pole of both these corrector magnets having the blue polarity. So their poles are opposite to the poles of the earth, so they reduce the directive force. In these conditions, with the vessel heading north or south, the corrector magnet reduce the directive force because their poles are opposite to the poles of the earth. But this reduction is very weak. Why is the reduction weak? The reduction is weak because our compass is at broadside on position to the corrector magnet. Now we know at broadside on position, the magnitude or the strength of the magnetic field is half of the strength of magnetic field in the end on position. So this reduction in the directive force is having lesser magnitude. Now we will compare it with the vessel heading east or west. Let's move on to the ship heading east or west. So this much is understood, beta. Now you can see the ship heading in a easterly or westerly direction. Now when the ship is heading east, you can see the corrector magnet being induced by the Earth's magnetic field, and our compass is located exactly midway between these two corrector magnets. Now you can see north of the compass we have a blue pole, and this blue pole matches with the blue pole of the earth. And south of the compass location we have a red pole of the corrector magnet, and this also matches with the red pole of the earth. So in this case, the poles generated on the corrector magnet are matching with the poles generated or the poles there on the earth. With both the poles matching, the sphere's corrector magnet increase the mean directive force at the compass location. And this increase is much more powerful as compared to the decrease. Why is this increase much more powerful? Because if you look carefully, the compass is at a end-on position to the corrector magnets. The compass is exactly in line with the axis of the corrector magnet, and being in line with the axis of the corrector magnet, the increase in directive force has a much more magnitude as compared to the decrease which was happening on northerly or southerly headings. The same thing is mentioned here again. Since the effect of a magnet is twice as powerful in the end-on position compared to the broadside on position, thus the increase in directive force is twice the decrease. Increasing the mean directive force leads to a reduction in the overall deviation. Based on the magnetic compass, these type of questions, they involve the concepts of magnetism and the concepts related to the coefficients. The question says, at Antofagasta, Chile, a ship was lying on a heading of 270 degrees. Maximum deviation was found to be 3 degrees east. If the permanent magnetism was corrected using forward and aft corrector magnets, state the possible reasons for getting this deviation and how it can be corrected. Now, before we go into the question, one important thing to understand in these type of questions is that when you have these type of questions, you cannot pick up their answers directly from the book. These questions basically test our understanding of the coefficients, understanding of the magnetism of the earth, magnetism of the ship, and you will need to apply your understanding to the question to find the solution. So let us go into the solution now and try to apply this. First, let us go into the formula for deviation. We are aware that deviation on any particular heading is given by coefficient A plus B sine course plus C cos course plus D delta sine twice the compass course plus eco cos twice the compass course. So using the coefficients, we can easily find out the deviation on any particular heading. Now let's try to analyze the deviation generated on the given heading. The heading given is 270. Now coefficient A, we are aware that it does not depend upon heading. It gives us a constant deviation on all the headings. So whatever is the heading, coefficient A is going to be present. So on a heading of 270 westerly heading, which is a cardinal heading, coefficient A is going to be present. So we mark a green tick mark here. Moving on to coefficient B, the second part of the deviation is given by B sine course. Now sine of 270 is -1. So in fact the deviation generated because of coefficient Prevost will be the highest on this heading. So this is also going to be present. Let us indicate this also by a green tick mark. We move to the third part, Charlie cos course, C cos course. Now cos of 270 is 0. So the deviation because of coefficient C on the westerly heading will be 0. So let us put a cross here. Moving on to the next part, we have D sine twice the compass course. Now D is also absent on all the cardinal headings. Sine of 2 into 270, that is sine of 540, is also 0. So this part of the deviation is also going to be absent because of coefficient delta. Coefficient delta is 0 on cardinal headings and maximum on intercardinal headings. Next we move on to coefficient eco. This part gives us E cos of twice the compass course. So eco is having its maximum value on cardinal headings. So this part of the deviation will also be present. Also cos of 2 into 270, that is 540, is also having a magnitude of 1. So coefficient E part of this deviation will be maximum. So we put a green tick mark here. So when you analyze the formula, you see three causes of deviation can be present: coefficient A, coefficient B, and coefficient E. Now let us try to analyze these coefficients one by one in detail. So the same thing is mentioned here. Coefficients generating deviation on 270 are A alpha, B Bravo. B would consist of two parts, and induced B. It can have both these components, and coefficient E eco. Now as far as coefficient A is considered, coefficient A is not generally present on normal merchant vessels, as we do not have any unsymmetrical horizontal soft iron on the ship. Whatever horizontal soft iron is present on the ship is symmetrical about the compass location. May it be the fore and aft longitudinal or the outward ship beam, both are symmetrical. So coefficient A is generally absent on normal merchant vessels. So the probability of deviation being generated by coefficient A is not there. Moving on to coefficient eco now, coefficient E. Coefficient E is also not generally present on normal merchant vessels, as we need horizontal soft iron symmetrical at 45-degree orientation to the fore and aft line for generation of coefficient eco. So usually on normal merchant vessels, we do not have any HSI at a 45 degrees angle to the fore and aft line. Whatever HSI we have on board, it is either fore and aft or athwart ship. It could be fore and aft longitudinal or athwart ship beam. So coefficient E is also absent on normal merchant vessel. So the probability of coefficient E also is not there. Now coming on to coefficient Bravo, coefficient B. Now in coefficient B, the question tells us the permanent magnetism was corrected using fore and aft corrector magnets. The forward and aft corrector magnets correct the permanent B part of coefficient Bravo. So it is mentioned in the question that PB has been corrected. The only option which now remains is the part induced B. So induced B is the most likely cause of this deviation which is being generated on the ship. Now this gets strengthened by the fact that there is no mention of correcting the induced magnetism in the fore and aft direction. The question doesn't tell us anything about correction of the induced magnetism. So this deviation which is generated is because of induced B. So let us how induced B can generate this easterly deviation. Now for this we need to be aware of that Antofagasta port in Chile is in the southern hemisphere. It is at about 23° south latitude. And in the southern hemisphere we are aware that the magnetic lines of force come out of the Earth's surface. So IB induced B, which is generated by VSI, vertical soft iron. If there is any vertical soft iron in the southern hemisphere, the lines of force, magnetic lines of force coming out of the Earth's surface will enter from the bottom, giving it a blue polarity, and will come out from the top end of the VSI, giving it a red polarity. So the top end of all the vertical soft iron in the southern hemisphere will be red. This top end is what affect our compass. So now let us make a diagram of the ship. You see the ship on a westerly heading. We have the compass needle also present here. North end of the compass needle has a red polarity, points towards the north, and the south end of the compass needle has a blue polarity. The question mentions that there is a 3° east deviation which is present. So let us show the deviation also. You can see this yellow color arrow showing the easterly deviation. Now for generating this easterly deviation, we know the top end of VSI in this southern hemisphere is having a red polarity. Now for a red pole to generate easterly deviation, it has to be west of the compass or forward of the compass. Let me show you. If you have a red pole in this particular location, as you see in the diagram now, this red pole is going to repel the red pole or north pole of our magnetic compass needle, and this repulsion is going to generate a easterly deviation. So a red pole is present forward of the compass or to the west of the compass. You see it is forward of the compass, it is closer to the bow side of the ship. So this is generating a easterly deviation. So this vertical soft iron has not been corrected. So that is why the easterly deviation is generated. Now there is one more possibility of having a red pole here. That possibility is that if we have corrected the induced P component of the ship, let us assume that there is a funnel aft of the compass needle and we have corrected it using a flinder bar. Now if the length of the flinder bar is more than what is required on that ship, so then the top end of the flinder bar is also going to generate a red polarity, which will be over and above the magnetism generated by the funnel. So that also can create a easterly deviation. So there are two possibilities. Either there is a VSI forward of the compass which has not been corrected, or if the correction has been made by a flinder bar, funnel correction has been made by a flinder bar and it has been put forward of the compass needle, The length of the flinder bar is more than required. In both these cases, we will have a red polarity forward of the compass towards the bow, and this red polarity, when the vessel is on westerly heading, is going to generate a easterly deviation. So this is the reason, and the question asks how it can be corrected. If it is a VSI forward of the compass, we have to place a flinder bar aft of the compass to cancel it. And if it is caused because of a oversized flinder bar, then the flinder bar has to be readjusted and the length of the flinder bar needs to be modified so that the correction is just right. The overcorrection has to be modified. Question on the screen now. The question says, on board a vessel with a constant 2-degree east deviation on all the headings, following permanent corrector magnets were observed, placed as given in the compass binnacle. Number 1, corrector magnet in the fore and aft direction with the blue forward and the red aft. Number 2, a corrector magnet in the authwardship direction with red on starboard and blue on port. Explain with suitable sketches what could be the reason for placement of correctors in the above manner. And part B of the question asks, what could be the reason for a constant deviation on all the headings? Let us now try to go into detail and understand the answer for this particular question. Now we are aware that the fore and aft corrector magnets, they correct permanent B coefficient of the ship. Now if we have a corrector magnet which has a blue end forward and a red end aft, it simply shows that the ship has a red bow and the blue stern. If the ship is having a red bow and we place a corrector magnet with the blue end forward or blue end towards the bow, this corrector blue is going to cancel out the red bow of the ship. Now a red bow and a blue stern happens when the ship is built on any northerly heading. Let me show this to you using a diagram. You can see a particular ship here. Now let us assume that this ship is being built in the yard on a northerly heading. If the ship is built on a northerly heading, we know that there is a red pole in the south part of the earth. Southern pole of the earth having a red polarity. The north pole of the earth has a blue polarity. Magnetic lines of force, they come out from the red pole and they go towards the blue pole. So this is the direction of the magnetic field lines. So if the ship is being built on a northerly heading, the magnetic field lines will be entering from the stern and leaving out from the bow. The part where the lines enter gets a blue polarity. That's why you see the stern of the ship has a blue polarity, and the part where the magnetic lines of force come out gets a red polarity. So that shows us the bow of a ship has a red polarity. So this tells us that the vessel is built heading north. Now moving on to the second part of the question. Authwardship magnets placed in the binnacle, they correct coefficient permanent C. The placement of the corrector magnet shows that the ship has a blue pole on the starboard beam or starboard side and a red pole on the port beam or the port side. You see, the question mentions that the corrector magnet is having its red pole to starboard. This red pole of the corrector magnet to starboard cancels out the blue pole of the ship on the starboard beam. Now, a ship which has a blue pole on the starboard side and a red pole on the port side, this kind of magnetism in the ship happens when the vessel is built on any easterly heading. Let me show you through a diagram. You see this particular ship which is built on a easterly heading. If the ship is built on a easterly heading, the south pole being the red pole, south pole of the earth being the red pole, magnetic lines of force come out of the south pole, they are going to enter through starboard beam. So starboard side of the ship is going to get a blue polarity. The question says that the corrector is having a red end to starboard. So this red end cancels out the blue pole of the ship, thus correcting coefficient permanent C. So the placement of the corrector magnet in this particular orientation, red to starboard and blue to port, immediately tells us that the vessel has been built on any easterly heading. Now, when we combine both these two factors, we come to know, combining above, we can infer that the vessel has been built on a northeasterly heading. The heading of the ship is having a northerly component, which results in a red bow and a blue stern, and it is having a easterly component, which results into the blue pole being on the starboard side of the ship and red pole being on the port beam or port side of the ship. So vessel has been built on a northeasterly heading, resulting in the ship's permanent poles being generated as they are stated in the question. Now moving on to the second part of the question, it says, what could be the reason for a constant deviation on all the headings? Now we are aware that a constant deviation on all the headings is generated by coefficient A. Continuous deviation on all the headings is generated due to coefficient A. So same is to be explained in this part of the question. You can make the deviation diagram for coefficient A and explain this diagram. That takes care of the second part. Coefficients of the magnetic compass, you will see that all these coefficients are denoted by positive or negative signs. We are now going to understand how this positive and negative sign is given to a coefficient. Now, to find out whether a coefficient is positive or negative, we have to check the deviation generated by that particular coefficient with the vessel heading in a direction between north and northeast. If the deviation generated is east, the coefficient is considered positive, and if the deviation generated is west, the coefficient is considered negative. So to determine the sign of a coefficient, assume the vessel on a heading between north and northeast and check the deviation generated by that particular coefficient. Deviation generated is east, the coefficient is considered positive. Deviation generated is west, the coefficient is considered negative. Let me show you by a diagram. Let us assume that we have a ship which is built on a northerly heading. So if a ship is built on a northerly heading, this red represents the red pole of the earth, the blue square represents the blue pole of the earth. Magnetic lines of force, they come out of the red pole and they go into the blue pole. The arrow shows the sign of the magnetic field lines. Now you can see these magnetic field lines are going to enter from the stern of the ship, and wherever the magnetic field lines enter, you get a blue polarity. So this particular ship has a blue stern. The magnetic lines of force are going to come out of the bow, giving it a red polarity. So this particular ship has a red bow. So a ship which is built on a northerly heading will have a blue stern and a red bow. Now let us try to take this ship on a heading between north and northeast and try to see what kind of deviation these poles generate. So we have placed the ship on a heading between north and northeast. The bow is having a red polarity and the stern is having a blue polarity. Now you can clearly see the red bow is going to repel the red end of our compass needle. Likewise, the blue stern is going to repel the blue end of our compass needle, and it is going to turn the compass in the anti-clockwise direction or the westerly direction. You can see this direction by the yellow arrow. So since a westerly deviation is being generated, this coefficient will be considered as negative. So this is basically permanent B coefficient, permanent B, and this will be minus PB coefficient. So you can summarize, minus PB coefficient is generated on a ship which is built on a northerly heading. Now let's try to analyze this for a ship which is built in southerly heading. You can see a ship which is built on southerly heading. The lines of force are going to enter from the bow now, so giving it a blue polarity. So we have a blue bow, and the lines of force are going to come out from the stern of the ship, giving it a red polarity. So the stern of the ship is red. Now let's take the ship on a heading between north and northeast. We see the ship heading between north and northeast. It has a blue bow and a red stern. Now if you look carefully, the blue bow is going to attract the red end of the compass needle towards itself, so generating a easterly deviation. Likewise, the red stern is going to attract the blue end of the compass needle. Moving, the compass needle is going to turn clockwise, generating a easterly deviation. So this coefficient, which is permanent B, will be considered positive, plus permanent B. So you can summarize, plus PB is generated on a ship which is built on a southerly heading. So the conclusion what we get from here is, negative PB or minus PB is generated on a ship built on northerly heading, and plus PB is generated on a ship which is built on a southerly heading. Analyze this positive and negative sign convention for coefficient permanent C also. Let us assume that we have a ship which is built on an easterly heading. A ship which is built on a easterly heading, magnetic lines of force are going to enter from the starboard beam, giving it a blue polarity, and they are going to come out of the port beam, giving it a red polarity. Lines of force come out of the south pole or the red pole of the earth, and they enter into the north pole or the blue pole of the earth. So a ship which is built on a easterly heading is going to have a blue starboard side and a red port side. Now let's take the ship on a heading between north and northeast. You see the ship heading in a direction between north and northeast. We have the compass needle present here. There is a blue pole on the starboard bow, starboard beam, and there is a red pole on the port beam. Now you can clearly see the red pole on the port beam is going to repel the red end of the compass needle. Likewise, the blue pole on the starboard beam is going to repel the blue end of the compass needle, turning it clockwise or generating easterly deviation. You can see the compass needle is going to swing as shown by the blue color arrow, generating easterly deviation. Now, since easterly deviation is generated, this will be called as plus PC, plus permanent C. So it can be summarized, plus PC is generated on a ship which is built on a easterly heading. Let us analyze this for a ship which is built on a westerly heading. So this ship is built on a westerly heading. We have the red pole, south pole of the earth represented by this square. We have the blue pole, the north magnetic pole of the earth represented by the blue square. Magnetic lines of force come out of the red pole, enter from the port beam, giving it a blue polarity. Wherever the lines enter, we get a blue polarity. The lines of force come out from the starboard beam, giving it a red polarity. Wherever the lines of force come out, we have a red polarity there. So this particular ship has a red starboard beam and a blue port beam. Let us analyze the ship on a heading between north and northeast now. So we have the same ship here heading somewhere between north and northeast. Starboard beam is red as mentioned in the top diagram, and port beam is blue. Now you can clearly see the blue port beam is going to attract the red end of the compass needle towards it, making the compass needle move anti-clockwise looking from top or generating a westerly deviation. This deviation is shown by the yellow color arrow here. Likewise, the starboard beam having a red polarity is going to attract the blue end of the compass needle, generating a westerly deviation. Now, since a westerly deviation is being generated, this will be considered as negative. So this is negative PC, negative permanent C. So negative permanent C is generated on a ship which is built on a westerly heading. So this is how we can find out the sign of any coefficient using the deviation generated on a heading between north and northeast. So the question is in three parts. Part A of the question says, if a ship has negative PB and a positive PC, in which quadrant was she heading when built? Part B of the question says, if the directive force on northerly heading is greater than the directive force on southerly heading, what coefficient is present and what is its sign? And the third part of the question says, if directive force on easterly heading is greater than directive force on westerly heading, what coefficient is present and what is its sign? Try to analyze and understand this question part by part. We go into the first part. If a ship has minus PB, negative PB. Now we just saw that a negative PB is generated on ships which are built on northerly headings. Let me again show you the diagram. You can see we have a ship which is built on a northerly heading. It has a red bow. If you take the ship on a northeasterly heading, this red bow repels the red end of the compass needle, generating a westerly deviation, which gives rise to minus PB. So question says that the vessel has minus PB. So minus PB is generated on a ship which is built on northerly heading. So this simply tells us that the heading of the ship on which it was built has a northerly component. So whatever heading she was built on certainly had a northerly component. Now the question says that the ship has positive PC or plus PC. Positive PC is generated on ships which are built on easterly heading. So let me again explain this to you using the diagram. You have a look at this particular ship which is built on an easterly heading. It has a red port beam and a blue starboard beam. Let us take this ship on a heading between north and northeast. So you see here the vessel is heading between north and northeast. You can see that this red port beam repels the red end of the compass needle, generating a easterly deviation, making it plus PC, plus permanent C. So plus PC is generated on a ship which is built on a easterly heading. Now combining both these factors, it clearly tells us that the vessel is built heading in a northeasterly direction. Whatever is the heading of the ship at the time of shipbuilding, it has to have a northerly component which gives rise to minus PB, and it has to have a easterly component which gives rise to plus PC, thus explaining that the vessel is heading on a northeasterly direction when it is built. Okay, up to here, beta. The second part of the question. Second part says, if directive force on northerly heading is greater than directive force on southerly heading, what coefficient is present and what is its sign? Let's try to analyze this statement. Now, directive force on a northerly heading can increase only if the ship has a blue color bow or blue polarity bow. Now, let us understand this using a diagram. Now, I have a ship here and I have placed the ship on a northerly heading. The question says that the directive force on a northerly heading is greater. Now, for the directive force to be greater, the ship's pole should match with the Earth's pole. Now, we know in the north magnetic pole of the Earth, we have a blue polarity. So, north of the compass needle, we should have a blue ship's pole. So, that is only possible when the ship has a blue bow. It is indicated by the blue pole in the diagram now. And at the same time, south pole of the earth has a red polarity. So if we have a red pole south of the compass needle, it is going to increase the directive force. So a increase on directive force on northerly heading would happen on a ship if the ship has a blue bow and a red stern. Now if a ship has a blue bow and a red stern, which coefficient does it have? Let us try to take this ship on a northeasterly heading. The same ship is now taken on a northeasterly heading, and you can see this heading. It is somewhere between north and northeast. The blue bow is going to attract the red pole of the compass towards it, generating a easterly deviation, telling us that it is a positive permanent B coefficient. Magnetism in the fore and aft direction generates coefficient Bravo. This is permanent B coefficients because these are permanent poles of the earth, permanent poles of the ship. So this explains that a vessel whose directive force increases on northerly heading has a positive PB coefficient. So the answer to this part will be positive permanent B coefficient. Now we move on to the third part of the question. It says if directive force on easterly heading is greater than the directive force on westerly heading, what coefficient is present and what is its sign? Now directive force on a easterly heading can increase if there is a blue pole on the port beam of the ship. Let me explain this to you using a diagram. We have a ship here which is on a easterly heading, and the question says that the directive force on a easterly heading is greater. Now for the directive force to be greater, the ship's pole and the earth's pole should match. So north of the compass we have a blue pole of the earth. The earth's north pole has a blue polarity. So the ship's pole also has to be blue. North of the compass, the ship's pole has to be blue. So if you have a blue pole on the port beam, it matches with the blue pole of the earth, increasing the directive force. Likewise, if you have a red pole on the starboard beam, it matches with the red pole, south magnetic pole of the earth, and increases the directive force. So the fact simply tells us that the ship has a blue port beam and a red starboard beam. Now magnetism in the athwart ship direction generates coefficient C. It is generated by coefficient C. So this ship has coefficient C, and this is permanent magnetism. So this is permanent C. Let us now try to find out whether this is positive or negative. So for this, we take the ship on a heading between north and northeast. You can see the same ship here heading somewhere between north and northeast. It has a red starboard beam and a blue port beam. And you can clearly see the blue port beam is attracting the red end or the north end of the compass needle towards it, generating a westerly deviation. So westerly deviation means it has a negative sign. So this coefficient is negative PC. Negative PC is generated on a ship which is built on a westerly heading. So the answer to this particular question is that the coefficient present on the ship is negative PC. If the directive force on easterly heading is greater than the directive force on westerly heading, the coefficient present is negative PC. On board your vessel, you notice that a deviation curve of magnetic compass has an easterly bias. That is, the deviation values are more easterly than westerly as the vessel is swung around in 360 degrees. Analyze and discuss in detail the causes of such a deviation curve. So let us first of all try to understand what the question wants to convey. Let us assume that on a particular ship we go and we see the deviation curve. A normal deviation curve is going to look like something like this, like a sine curve. At a particular heading, the deviation is nil. Then as the heading changes, the deviation increases, goes to a maximum value. In this example, we have taken 5 degrees east. After that, this starts to reduce and then crosses over to the western side. The maximum westerly deviation occurs here, 5 degree west, and then it again becomes 0. So over the course of entire 360 degrees, this curve shows how the deviation of the ship changes. Now the question says that on a particular ship it has an easterly bias, that is deviation values are more easterly than westerly. So let me show you what the question means. Now you see a different deviation curve, and this deviation curve, if you notice, it has shifted in the easterly direction by this much value. You see this yellow color arrow. Basically the curve has shifted to the eastern side. The right side is the easterly deviation. So it has shifted to the easterly side by a fixed value. Let us assume that it has shifted by 2 degrees east. So what is the cause of such a deviation curve? Now we can see if you check the deviation at any particular point, it will be the deviation in the previous curve plus a value of 2 degrees east. So it was 0 here, nil, and if you look at it here, it is 2 degrees east. It was maximum value was 5 degrees east, and if you look here, it will go up to 7 degrees east. So you see a constant difference in all the deviation values towards the eastern side. Now, what could be the cause of such a deviation? We know of all the coefficients, there is one coefficient which is constant, does not depend upon the heading of the ship and remain constant over all the headings, and that is coefficient A. So this is the coefficient which is present in this particular ship, coefficient A. It has a value of 2 degrees east, and this coefficient A, if it is present on a ship, is usually not shown in the deviation curve. It is applied as an index error. So you can have a normal curve like this, and the compass adjuster is going to mention that coefficient A here is 2 degrees east. So this 2 degrees east can be applied to the value of deviation at any particular heading, and it will give you the deviation for that particular ship. So we need to explain the coefficient A in this question, making the deviation diagram and explaining the deviation on all cardinal and intercardinal headings. You have noticed that the Flinders bar is attached to the binnacle in a relative slewed direction. That is 015 degrees instead of usual direction of ship's head. Part A of the question asks, analyze and discuss the reason for such an arrangement. And part B asks, what would have been the ship's heading on which the maximum deviation occurred prior to the Flinders bar correction. So let us first try to understand the meaning of the question. Let's make a diagram of a ship. You can see a particular ship here. We have shown the binnacle. We have shown the fore and aft line. You can see this dotted line here, the fore and aft line. And we have also shown the athwartship line here to have a sense of directions. Now the question says the Flinder bar is attached to the binnacle in a relative slewed direction of 015 degrees. Now the 015 degrees is basically the relative direction of the Flinder bar with respect to the ship's head. So from the ship's head, if you go 15 degrees, let me show you here in the diagram. You can see from the ship's head, if we go 15 degrees, the relative bearings are measured clockwise from the ship's head. So if you go to this 15 degrees direction, this is where the Flinder bar lies. You can see this yellow color flinder bar shown in the diagram now. So first part of the question says, analyze and discuss the reason for such an arrangement. Now on a usual ship, the flinder bar opposes the vertical soft iron present on the ship. On a normal merchant vessel, the main vertical soft iron, most predominant vertical soft iron which we have is the funnel. The funnel is usually exactly aft of the compass. So to compensate the funnel's effect, the flinder bar is fixed up just forward of the compass. But in this case, the flinder bar is slewed 15 degrees. Now that means that the magnetic field generated because of vertical soft iron is not aft of the compass. The magnetic field which is generated must be opposite to the direction where the flinder bar is. So that means that whatever magnetic field is there on the ship because of vertical soft iron will have a resultant direction opposite to where the flinder bar is. So as you can see, this red color arrow shows us the direction of the resultant magnetic field caused because of vertical soft iron. So if the vertical soft iron causes a field in this direction, in the direction of the red arrow, the flinder bar is fitted. The yellow color round represents the flinder bar, will cancel its effect, and the compass will be corrected. Now, how can we have the resultant in this particular direction? Now we are aware that exactly aft of the binnacle we will have the funnel. So you can see the funnel now coming up in the diagram. So funnel will be exactly aft of the binnacle. The resultant is slightly towards the port quarter. So that simply tells us that there has to be a vertical structure on port side of the compass or port side of the binnacle. You can see a vertical structure now coming up towards the port side of the binnacle. So the resultant of this vertical structure and the funnel falls in the direction of the red arrow, and this resultant is what is our flinder bar correcting. So that brings us to the answer of the first part of the question. The first part answer basically is that the flinder bar is slewed when IC induced C is also present along with IB induced B. So that tells us that there is a vertical structure on the port side of the compass. Any vertical structure to port or starboard of the compass generates induced C. So this is the analysis for the first part of the question. Now the second part of the question says, what would have been the ship's heading on which the maximum deviation occurred prior to the Flinders bar correction? The meaning of this question, part B, is that we have seen that the resultant of IB and IC, funnel and the vertical structure, lies in this particular direction, in the direction of the red arrow. Now, what is the heading on which this resultant would cause maximum deviation? Now, for any magnetic force to cause maximum deviation, it should act at right angles to the magnetic needle. You can see it here also. Maximum deviation because of any force or magnetic field occurs when that force, in our case, the resultant of IB and IC, which is the red represented by red arrow. So maximum deviation occurs when this resultant acts at right angles to the compass needle or at right angles to the magnetic lines of force which run in the north-south direction. You can also represent it in this way, that the maximum deviation would occur when the resultant should lie exactly east or exactly west of the compass. So if we take the ship on such a heading that this resultant goes to exactly east or west of the compass, that is the heading on which the maximum deviation would occur. So let us see that now. The first option of bringing this resultant to port or starboard of the compass is that if the resultant moves in the direction of the yellow arrow by this much of an angle, it would come exactly west of the compass needle. Now the angle represented by this yellow arrow is 75 degrees. You see the flinder bar was lewd 15 degrees. So the remaining angle between the stern of the ship and the port beam of the ship is 75 degrees. So the resultant would come in direction west of the compass if we swing by 75 degrees in the clockwise direction. That basically means that if the ship alters its course to starboard by 75 degrees, you can see this green color arrow representing a 75-degree starboard alteration. That is the heading on which resultant will be at right angle